All right. So,
What's this colorful thing?
so we talked about eddy currents. Yeah. Have you heard about something called eddy current testing? Have you heard of something called non-destructive testing? What does that, when you hear that word, what do you imagine in your head?
Non-destructive.
Non-destructive testing.
Destruction, I know. So that way non-destruction is also not there. So you are not destructing that object while testing.
Right. The target object.
That's what I could make out from this
Yes.
English.
Yes. But I think you also mentioned, I think in the first couple of classes, remember you said you should not do any modifications to the thing that you
To the measurement.
Measure.
Yes.
Right. So non-destructive in this case means you're not doing that.
Yeah.
Right.
Yeah. That statement applies to all kinds of measurements.
Yes. But sometimes
this is again a special case.
Well, sometimes you have to, let's say, for medical applications, sometimes you have to insert the sensor inside the body, right? So you are being, but that's more like non-invasive and non-invasive.
Yes.
Right?
Yes.
That's a little bit different to, I think, non-destructive testing.
Yeah.
Right. But
that also people prefer if it can be done without.
Of course. I mean, I'll be the same, right? Someone's going to insert something in me, or you can do it
because there is no better solution. This is
yes.
Yeah.
So this eddy current testing is actually one of the most critical testing techniques in non-destructive testing. Okay, so if you look at here,
so it is something to do with the diagrams that you have shown before.
Yes. So we talked about eddy currents.
Eddy currents you have shown.
Yes.
Yeah.
So now we are.
But what are we testing?
We'll talk.
You're coming to that.
Okay. Right. So eddy current, but we are using these eddy currents now. Before we used it, just to simply to detect. That's it. Right. If there's a metal or something of interest underground, okay, or in the airport. But now you're talking about something called non-destructive testing or non-destructive evaluation. So you're evaluating something now, okay, not simply detecting. Now, obviously, this huge market, right? You have like top companies like GE, Zetec, IBG, many companies, right? And there's in 2023 it was a 372 million market, growth rate of 5.7%. And you can see there are a lot of different types of eddy current testing: conventional eddy current testing, alternating current, pulsed eddy current, remote field testing, used in a lot of different industries. But eddy currents, the problem with eddy currents is that there are a lot of variables. Now, we only talked about conductivity, permeability, and frequency. But eddy currents depend on conductivity. We talked about that. Magnitude of the primary magnetic field, permeability, geometrical variations.
Yeah.
Okay. The magnetic coupling
between
the primary coil and the material. Okay. Again, we'll talk about that a little bit later. Inhomogeneity, right?
Of the material.
Right. Now we are thinking, okay, it's the conductivity is the same, but it could be a matrix, right? Anisotropic. Then got a little bit difficult. The test frequency, we talked about that. And the skin effect, again, we talked about that, right? So these are some of the variables. And again, you have some things like temperature that I have not mentioned here.
Yeah, but kind of it is there in the conductivity.
Yes. True. Okay. Now let's look at eddy current testing a little more. What is eddy current testing, right? So here, let's say you have some object, some material here.
The metal. It's a metal. It's a conductive object.
Yeah, let's say it's a conductive object. Or should we say conductive object?
Yeah, conductive or ferromagnetic is also fine. And it can be a poor conductor, but if it has good permeability, that's also fine.
Yes. But if it has both, it's a problem.
Yeah.
Material. Okay? Yeah. Now, what did we talk about before? We said We have a coil,
Yes.
produce a magnetic field, which is this one.
Yeah. And
Primary
it's a
magnetic-
time varying magnetic field.
Time varying magnetic field,
If I give just DC, nothing happens. Yes.
right? According to Maxwell's equations. Remember.
Yes.
So this is a time varying field. Okay. Then you get a secondary field,
Yeah.
okay, from the eddy currents.
Correct. It opposes the other one.
Opposes the other one.
So the overall field reduces.
Yes. So then you have an overall field here. HR.
That is lower than what was originally generated by the coil.
Yes.
That means inductance will reduce.
Yes. Well, technically, yes. So if we are to draw this, okay, then let's say we have some alternating current source. We have our inductance, resistance.
Yeah.
There's some current flowing here.
So this is the coil. This is this excitation coil.
This is the excitation. Okay.
Yes.
Okay.
Or surge coil. What?
Yes. So let's assume here that we are using the same coil for excitation and detection.
Yeah.
Right. Even though the graph has another coil here, but let's just assume.
Yeah.
For okay. Yeah. Same coil. Then your impedance will be
Impedance of
the coil.
that coil.
Yes. Will be x squared plus r squared. Right. Now, when this primary coil changes, right? Primary magnetic field changes because of the secondary coil, right? What happens there?
XL will reduce.
XL. But let's say, if you're measuring if you have a material, okay, that has a okay, no, let's do it this. Now let's say you are increasing conductivity.
Okay.
So you have material, but you're increasing the conductivity, and you're watching and you're looking at your impedance. Okay. Let's say you're slowly increasing your. Then what's going to happen to your impedance if you're increasing the conductivity? Right. Let's say from 1 to 10. These are just values, huh? Let's say 1 to 10. Then what's going to happen? What are you going to observe if you watch this? First of all, when you increase the conductivity, that means more eddy currents are going to be on surface.
Yeah.
Agree?
Correct.
Then what does that mean? That means that this HS value is going to
increase the pace.
That means
that last one you drawn is the smaller.
Yeah. Correct.
Yeah.
Why? Because obviously that
position is small.
Which means that the magnetic field that your inductor, R, is exposed to becomes lower and lower and lower.
Yeah.
So technically your XL will decrease.
Yeah.
Correct? So Z will decrease, you said. XL will decrease. What about your resistance? What's going to happen to your resistance?
Resistance of the coil.
Coil.
It's the effective resistance.
Effective. So I'm talking about the resultant.
So that means, let's say there is some power loss. I mean, there is eddy current in the object. Current is flowing. So there is some power loss.
Yes.
So this loss has to be represented in the excitation coil somehow.
Yes.
Correct?
Yes. 100% correct. Which means your resistance will increase. Right? That's clear. Huh? Now, what if this is clear, but I should have just taken one by one. But anyway, when your conductivity decreases, right, then what's going to happen? When your conductivity decreases, the amount of eddy currents flowing will also decrease.
Yeah.
Right? So your impedance will increase.
Yeah.
That means your coil will now also see a higher
magnetic field,
which means the inductive reactance is going to increase.
Compared to the earlier one.
Yeah, compared to this one, right? So they're two different things. Here we are now increasing the conductivity of materials, testing the different materials. Here we are decreasing the conductivity of materials. So then Z increases, XL also increases because it's seeing more magnetic field now. But your R then, as you said, now opposite will decrease. Right? So this is a very basic way of, let's say, if you want to look at conductivity. And again, here, I must say that we are keeping mu the same. Mu is the same. But if I give you material, okay, and you see Z is changing, let's say I'm giving you, three different materials, okay? Material 1, 2, 3.
Yeah.
And your Z is, let's say, increasing.
When I move from one object to the other,
Yes.
the coil, I'm exposing to the coil.
Here first.
Yeah, got it.
Right? And then this way.
Yeah.
Let's say Z is increasing. So from here we know. Fine. But can you say, but you don't know the conductivity or the permeability of these materials. Now, but all you know is that you're getting a different Z for that. Can you separate the variables? Can you say, oh, this is increasing because of conductivity? Or if this is increasing because of mu? Can you separate the variables?
Seems to be difficult.
It's very difficult, right? So this way of evaluating material is good if you just want to see the different types of materials, right? But if you want to separate the variables and say, oh, here we are actually measuring the conductivity, or here we are measuring the permeability, then this is not the best method.
Correct.
Now, of course, one method is you can, if you have a mu material, you can drive it to saturation. Then you're only left with your conductivity. No? So whatever you measure will be related to conductivity.
Then the excitation coil has to be operating at very high current.
Correct. Yes, in that case.
But you said if you drive it to saturation, the mu R will be 1 almost.
Yes.
May not be that obvious to. For me, it is not obvious.
Why it's 1?
Yeah.
Okay. So
because I think that BH curve, we have not.
No, that comes in the
later.
next, like with flux gate, right? But generally, what happens, right? When you have a magnetic material with a certain permeability, you apply a magnetic field, right?
It gets magnetized.
You
increase the magnetization or more current.
Yes.
It gets magnetized more.
Right. So it kind of grows.
Yeah.
And then what happens?
After some time, it's like I'm studying a lot. I cannot study anymore.
And you're empty.
Yes.
No, it's the same thing, right?
Yeah.
So basically, we'll talk about the VH curve a little bit later. But the whole idea is, if you have a certain material, right? I'm just drawing a sphere here. You apply a magnetic field, the magnetic fields will converge here. So here, right? Now, if you keep increasing this H, okay? Now, this will go and converge, and at one point, it will reach saturation, but it will just flow like this. There will be nothing there. So then, the permeability of this, so this magnetic fields converge to this mu. Why? Because there's a certain mu value here that's much higher than air. But once that is saturated, right?
It is like air.
It is like air. So that's why. So here, when I say if you drive it to saturation,
yes,
that's what I meant. But as you said, that brings its own challenges.
Yeah.
The primary coil has to be
very large
to
drive it to saturation.
Again, it depends on the material, I suppose.
Yes,
right?
Yes.
But
also, some materials, the permeability is a function of the frequency.
Yes.
So sometimes if you, depending on the material, if you measure at two frequencies where you have different mu R, That also may help you
yes.
to identify
Yes.
whether it is due to sigma or
Yes. But what you must say, there's a better method. By looking at this, do you think there's a better method?
to say 1, 2, 3, is it
Yeah.
due to conductivity or due to permeability? Yes. I don't.